Good morning, students. Today's topic is the design of FIR filters. So here to design the FIR filter frequency response is needed based on the n value and the nature of the impulse response of the FIR filter. There are 4 possible types. So case 1, case 2, case 3, case 4 already discussed in the video 2. For each case we should determine the frequency response. So I have tabulated all these particulars in the table 1. Kindly follow this. This is the magnitude function mod of h of omega. For each case I have mentioned here. Now coming to the FIR filter design steps for different techniques. So here basically 3 different techniques are there to design the linear phase FIR filter. The first one is the window method, the second one frequency sampling method, third one optimum equi-ripple filter method. So here design steps for linear phase FIR filter using window method. First step is choose the desired or ideal frequency response, that is HD of omega. Second step is determine HD of n from the HD of omega by applying the inverse Fourier transform. Third step is convert or truncate the infinite duration HD of n to a finite duration h of n to get the FIR filter of length capital N. This truncation is obtained by multiplying the HD of n by a window sequence W of n. This W of n is called as window function. That means h of n is obtained by multiplying HD of n and W of n. H of n is equal to HD of n into W of n. Fourth step is find the h of z from h of n by applying the z transform. That is h of z, that is a transfer function of the digital filter. Last step is choose a suitable structure and realize the filter. So that means here to design the FIR filter, firstly we should consider the specifications. From that specifications find the HD of omega. Now from HD of omega find the HD of n by applying inverse Fourier transform. Now from HD of n find the finite duration impulse response h of n based on the window function, and then from h of n find the h of z. So for that h of z realize the filter structure. These are the steps here involved using window technique. Similarly we complete the remaining methods. So the second method is what is that? Design of linear phase FIR filters by using frequency sampling method. So here also first choose desired or ideal frequency response HD of omega. Now from HD of omega find the h of k. This is nothing but the sampled version of HD of omega is h of k. That means get h of k by sampling HD of omega at finite number of points, n point. Now determine the impulse response of the filter h of n from h of k by applying the n point inverse DFT. Now from h of n find the h of z and then realize the structure, filter structure. Okay, these are the steps by using frequency sampling method. Now coming to the third method, design of optimum equiripple linear phase FIR filter. So here basically the drawback in the FIR filter designed by using window and frequency sampling method is it does not have precise control over the critical frequencies such as passband frequency and stopband frequency. So to overcome that drawback, here we are going to Chebyshev approximation technique. So here by using this technique, you can get the ripples in both passband and stopband. This method is called as optimum equiripple method. Okay. Now for the exam point of view, window method is very important. Now see this. So actually here we don't know what is window function. So first we should concentrate on the window function. So now see here various window functions are there. That is rectangular window, Hanning window, Hamming window, Blackman window, Kaiser window, like that. So but every window should follow the two characteristics. The first one is for each window function we should calculate the frequency response. That frequency response main lobe width should be small. That means the total energy is actually contained in the main lobe. That's why the width of the main lobe should be small and it should contain as much of the total energy as possible. And of course frequency response range is minus pi to pi or 0 to 2 pi. So here the side lobes should decrease in energy rapidly as omega tends to pi. That means the frequency response side lobes are decreased as omega tends to pi. So here you should remember these characteristics to select the window. So here we have the different windows. For each window you should remember the frequency response and impulse response also. Okay, it's okay. Now here coming to the windowing operation, here one example I have placed here. Suppose this is the low pass filter frequency response. So the low pass filter frequency response is HD of e power j omega. So now suppose if you want to design this filter, FIR filter, so here this is the ideal filter. You should convert this one into the practical filter. So now here to get that one, we should multiply this HD of n into the W of n. Multiplication in the time domain yields the convolution between those frequency responses. Of course, from the frequency convolution property, we can understand this one. That means actually HD of n into W of n yields the convolution of frequency responses of individual. Now HD of e power j omega is this one. Suppose if I take any window function like this, that is W of e power j omega, if I convolve these two, I can get this type of characteristic. So what is this? If you observe, ripples are there here, stop band and the pass band also. Some transition band width is there. So that means which obeys the characteristics, practical filter characteristics. Okay, that's why here we should multiply HD of n with the W of n. Okay, now here coming to the window functions. So different window functions are there. So now here shortly I have tabulated in the table 2. For rectangular window, the window sequence is nothing but W of n is equal to 1 for the range minus n minus 1 by 2 to the n minus 1 by 2. I have written like this. The range is here capital N. So we may take like this 0 to n minus 1. Otherwise the range is minus of n minus 1 by 2 to n minus 1 by 2. Both are right. So then remember this one. W of n for rectangular window is equal to 1 for 0 to n minus 1. Otherwise 0. We may take in other way, that is W of n is equal to 1 for minus of n minus 1 by 2 to n minus 1 by 2. Otherwise 0. In the same way for triangular window, W of n is nothing but 1 minus 2 mod n by n minus 1 in this range, otherwise 0. For raised cosine window, this is the one. It involves two different windows. One is the Hanning window, another one is Hamming window for different values of alpha. Alpha is equal to 0.5 for Hanning window, alpha 0.54 for Hamming window. Now coming to the Blackman window, here the W of n is this one, and for the Kaiser window, W of n is this one. For each case, I have mentioned here the frequency response also, but very important one is W of n. All of you remember the W of n for each window, okay, to solve the problem. So this is the table 2. Remember that one. And table 3 here. Here I included this one. That means different filters are there. Low pass, high pass, band stop. For each case, frequency response, ideal frequency response is denoted like this. HD of omega is equal to actually 1 for a certain duration, minus omega c to omega c. Omega c is the cutoff frequency, and other than the period 0. But here we are considering the linear phase filters, not the zero phase filters. If zero phase filters are there, you take 1 here. But here we are considering linear phase filters. So you take the e power minus j omega alpha. So HD of omega is equal to this one for low pass filter. For this, if you apply the inverse Fourier transform, you can get the HD of n. That's why here I am writing the equation for that. Inverse Fourier transform equation 1 by 2 pi integration minus by 2 pi HD of omega e power j omega n d omega. So here for this specifications, or for this low pass filter frequency response, HD of n is equal to 1 by 2 pi integration minus omega c to omega c e power minus j omega alpha e power j omega n d omega. Okay. Now coming to the high pass filter, band stop filter for designing purpose. So here you should know the HD of omega and also how to solve the HD of n. Okay. So that's why here this table 3 is important. Kindly follow this. Next one is table 4. Here for what I said earlier, zero phase filter is there, linear phase filter is there. In the case of zero phase filters, HD of n formulas included here. For the linear phase filter also, I included the formulas HD of n. That means based on this equation, if you solve the particular what is that HD of n for each HD of omega, you can get the formulas like this. Okay, for each case, so I have included, you should follow this, and this is important to design the FIR filter. So now we have the 4 tables, table 1, table 2, table 3, table 4. These 4 tables are involved to complete the designing the FIR filter. Okay. Now coming to the problem, first problem, that is the design a low pass filter using rectangular window by taking 9 samples of W of n and with a cutoff frequency 1.2 radians per second. So this is the problem given. So now from this problem, firstly note down the given particulars. So here the given values are cutoff frequency. What is that? Omega c. That is equal to 1.2 radians per second. Now how many samples are there? 9 samples. That means omega W of n width is 9. That means capital N is equal to here 9. So what is the here filter? Nature low pass filter. So here note down all the things given: cutoff frequency, n value. Now low pass filter means what is the HD of omega in the case of linear phase filter? That is e power minus j omega alpha, in between the minus omega c to omega c, otherwise 0. For this, see the table 3 and table 4. Okay. So here HD of step again here we should calculate the HD of n from HD of omega. HD of n is equal to inverse Fourier transform of HD of omega. Use this formula and then find the HD of n. So these particulars are included in table 3 and table 4. So if you have an idea, you can directly take the equations HD of omega and HD of n equations. Otherwise, you may solve here by using formula. Okay. It's okay. Now here, if you observe this one, HD of n is equal to sin omega c n minus alpha by pi into n minus alpha. So here, if you substitute n is equal to alpha, so n is equal to alpha. So here alpha is nothing but n minus 1 by 2. So here HD in the HD of n, for different values of n, we should find out the coefficients like HD of 0, HD of 1, HD of 2, HD of 3 and so on. So here if you substitute HD of alpha, n is equal to alpha means capital N minus 1 by 2. Suppose in this case n is equal to 9, alpha is nothing but 9 minus 1, 8 by 2, 4. That means at n is equal to small n is equal to 4, sin omega c, here n minus n is 4, alpha also 4. 4 minus 4 gives the 0. Sin 0 is 0. Pi into 4 minus 4 means 0. 0 by 0 is indeterministic form. To avoid that one, at that particular case, n is equal to alpha case, you should apply the L'Hospital rule. Then you can get the equation like this, omega c by pi. Okay. So do it, and if you have doubt, ask me. Okay. So now for each case, for each filter, actually HD of n, in HD of n, you should segregate like this. N is not equal to alpha, what is the formula? For n is equal to alpha, what is the formula? Okay, by using this LH rule. Now, here coming to the next point, what is the third step? Actually, what is the next design step? So, after finding the HD of n, we should find out the H of n by using the formula HD of n into W of n. What is the W of n here? Window function. What is the window function here? The given is rectangular window. Use the rectangular window. So that means here the rectangular window is WR of n, that is equal to 1 for n 0 to n minus 1. Otherwise you may take minus of n minus 1 by 2 to n minus 1 by 2. Okay. So here I am taking 0 to n minus 1. Okay. So omega r of n is equal to 1 in this duration. Otherwise 0. Now what is the h of n here? Just multiply these two. HD of n and W of n. So that means h of n is equal to 1 into HD of n is nothing but HD of n in this duration 0 to n minus 1. Otherwise 0 into HD of n is 0. That's why h of n is equal to HD of n for n is equal to 0 to n minus 1. So here for the window sequence, see the table 2. Suppose if they ask Hamming window, Hanning window, triangular window. So here from the table 2, you just take the equation and then multiply that equation with this hd of n and then write the equation h of n. Okay, h of n is equal to hd of n. So now here n is 9. So omega c is 1.2. Alpha is n minus 1 by 2 means 4 value. 9 minus 1 by 2, 4. Now find the all coefficients. Impulse response coefficients. What is that? n0 to n8. Substitute h of 0, h of 1, h of 2 like that. So here in the formula substitute, then you can get the answers like this. So here keep in mind, here omega c is the 1.2 radians per second. That means this is in radians. Use the radians. Okay. Now you can get the answers. Check it once. If you have any doubt, ask me. So here, be careful here at n is equal to alpha case. You don't substitute value in this equation. You can get the 0 by 0 form. That's why here, so at n is equal to alpha, that means at n is equal to 4, use the formula omega c by pi. From that formula, find the answer. Okay. So h of 0 to h of 8, we have the coefficients now. Okay. So now the next step is here, for h of n here, find the h of z. Before going to that here, so here impulse response h of n is there. So here we should identify the type of that impulse response. Okay, based on these coefficients, so you may easily understand that h of 0 is here, h of 1 is this one, this h of 1 is repeated here, h of 7 in h of 7, h of 0 is repeated in h of 8, h of 2 is repeated here h of 6, like that. That means here it follows certain symmetric condition. So here from this we can conclude that the impulse response is satisfying the symmetric condition. What is the symmetric condition? H of n is equal to h of n minus 1 minus small n. So here, so we may check like this. So h of capital N minus 1 means 8. H of 8 minus n is h of n. So now, so I am substituting here. N is equal to 5, 6, 7, 8. H of 5, 6, h of 7, h of 8. H of 5 is nothing but from this formula h of 3, h of 6 is h of 2, h of 7 is h of 1, h of 8 is h of 0. So now here it follows the symmetry condition. So now, so coming to the magnitude function, mod of h of omega, see the table 1 for the impulse response symmetric and n is odd case. What is the magnitude function? H of n minus 1 by 2 plus summation n is equal to 1 to n minus 1 by 2, 2 into h of n minus 1 by 2 minus n cos n omega. So that's why here, so I told you, remember the table 1. Okay. So that means see table 1 here and then note down. And now mod of h of omega is equal to, substitute here n is equal to 9 and then simplify and then substitute all the coefficients and then you can get mod of h of omega like this. Okay. Now 6, next point is the 6 here. That means finding the h of z. So now h of z is equal to summation h of n z power minus n. So here I have to realize the filter. So now mod of so here from the 5 you can conclude that the frequency response of the filter is available. Now here I am doing the filter structure. So now here for that I have to find out the h of z. So h of z is equal to this one. Now here, so we know that it satisfies the symmetric condition. So that's why I am writing here 0 to 3 and 5 to 8. So samples are repeated. Now I am separated this middle one and now I am writing like this, summation n is equal to 0 to 3 h of n z power minus n plus h of 4 z power minus 4 plus summation n is equal to 5 to 8 h of n z power minus n. Of course, these are equal. So that's why here these are equal to 0 to 3. That's why write 0 to 3 and h of n, but z of minus of n minus 1 minus n. So write like this, z power minus of 8 minus n. What I am doing, what I did here actually, I am taking this third term and I am substituting here at n place m minus capital N minus 1 minus m, capital N minus 1 minus m. Okay, so and then after simplification I can get this, but logically if I think I can write like this also. Okay, summation 0 to 3 h of n z power minus of capital N minus 1 minus n shortly. Okay, now this is nothing but z power minus of 8 minus n. Now common this and then simplify like this. Now find the digital structure. To do that I need y of z. That's why from h of z transfer function I can get the y of z. So now h of z is equal to y of z by x of z. So take the equation and cross multiply, and now y of z is equal to this one. Okay, for this I am using the linear phase realization structure. So this is the digital structure. Okay, so for this kindly go to the unit 3 and then so just read once, and then from h of z you know that how can you realize the filter using linear phase realization. You just follow that one. Okay, this is the one here, how to design the FIR filter. Okay, this is the problem here. So we solved. Now what is that? Design a low pass filter. In the same way we can expect the questions like that. Design a high pass filter, band pass filter, band stop filter using different window techniques. Okay, right? So for this here we need the information and from the tables 1, 2, 3, 4. Okay, kindly follow that and then substitute and then first do the practices and then learn. Okay, now coming to the next one. So just this is the assignment question. Design a high pass filter using Hamming window by taking 9 samples of W of n and with a cutoff frequency 1.2 radians per second. So just do this and then if you have any doubt ask me. Okay, now this is another one also here I have included. That is, suppose filter is not mentioned here, but they give the equation directly, hd of e power j omega is so and so like that. So here in such a case how can you deal the problem is knowing is very important. That's why here design a filter with hd of e power j omega. Here e power minus j3 omega is given minus pi by 4 to pi by 4 duration. Okay, use the Hamming window and samples are n7. So solution also added. Now I send the PPT to you. You just check. Thank you.